Okay, good afternoon, everyone. My name is Sungmin Hong, and it is my great pleasure to be here as an invited speaker of A-World 2024. The title of my talk today is Extension of Simulation Capabilities of Advanced Transport Solvers. This is outline and introduction. Since this A-World workshop is mainly for device engineers, I think that I don't have to re-emphasize the importance of TCAD technology, computer-aided design. TCAD tools are indispensable for semiconductor R&D process, and they are being used every day by device engineers. By performing the process simulation and emulation, we can check the feasibility of a given fabrication process. As a result, we obtain a device structure with dopant and stress profiles. By performing the device simulation, we can even try to estimate the electrical properties of a given device structure. In this CFET example, we have a bottom tier P MOSFET and a top tier N MOSFET. The DC-IV characteristics and time-dependent responses can be calculated. The device simulation results are used to optimize the semiconductor technology. Then, what is the underlying principle of the device simulation? The electric current is directly related with charge carriers, such as electrons and holes. Charge carriers generate the electric field, and this generated electric field once again accelerates the charge carriers. Simply speaking, we must solve the Poisson equation for the electric field and the transport equation for charge carriers in a self-consistent manner. However, there are several models for the carrier transport. That's the reason why we have the model hierarchy. From this figure drawn by the Intel engineers, we can find that still the simple drift diffusion model is the main workhorse of contemporary TCAD device simulation. At the same time, we can find the advanced transport solvers, and they are used as reference tools for the drift diffusion model. Let me briefly explain those advanced transport solvers. The first one is the non-equilibrium green function NEGF. It is a standard model for quantum transport simulation. The central quantity is the retarded green function, and it describes the coherent propagation of the electron wave function. Of course, there are several mechanisms to break this coherent wave propagation. These effects are modeled as self-energies. By combining them all, we can calculate the lesser green function, and it contains the energy spectrum of electron density. Although it looks a little bit complicated, the NEGF solver has been actively applied to the simulation of nanoscale MOSFET. Another advanced transport solver is the multi-solvent Boltzmann transport equation solver. Since it is just a semi-classical transport solver, it cannot consider the coherent wave propagation. However, it can include the quantum confinement effect by calculating the solvent structure. For example, from this three-dimensional device structure, we generate several cross-sections along the channel direction. Then, for each cross-section, we solve the Schrödinger equation to calculate the solvent structure. The one-dimensional carrier transport is simulated by solving the solvent-wise Boltzmann transport equation. Although it is a semi-classical transport solver, the Multisolve and the BT solver is regarded as a good compromise between physical accuracy and numerical efficiency. Yes, these advanced transport solvers are much more advanced than the conventional drift diffusion model. Therefore, one may guess that these solvers provide flexibility in terms of simulation capabilities. However, actually, it is not the case. As shown in this comparison table, these advanced models are mainly restricted to the DC simulation. It is because for general cases, their equations becomes too complicated or numerical solutions are difficult to calculate. In this presentation, I will share my recent effort to extend the simulation capabilities of those advanced transport solvers. Presentation materials are mainly taken from two recent IDM abstracts, and in this presentation, I will try to deliver my result without any equation. It is noted that all of my results are obtained by using my in-house device simulator. First, the AC NGF simulation. In the smooth signal analysis, we assume a voltage excitation with an angular frequency omega. When the magnitude of this voltage excitation is small enough, we have a linearized system. By solving this linearized system, we can calculate the response with respect to the voltage excitation, such as the Y parameters. Even for the NEGF simulation, the procedure is the same. First, we obtain the DC solution. Based upon the DC solution, a linearized system is identified and solved. The linearized NEGF equations can be found in references and not repeated here. And as I told you before, the central quantity of the NEGF simulation is the retarded Green function for coherent wave propagation. For the DC NEGF, the potential is static and the retarded Green function is a function of a single energy level. In the AC NEGF, since the voltage excitation introduces an additional time dependence, two different energy levels separated by half omega are coupled. The voltage excitation at the terminal introduces the potential fluctuation inside the device. This potential fluctuation, delta phi, can affect the retarded Green function. Therefore, when we implement the AC NGF simulation, influence of the potential fluctuation on the Green functions should be evaluated accurately. When we do it without any mistakes, we can expect the current conservation. As shown in these figures, the perfect current conservation can be observed at various frequencies and various bias conditions. I would like to stress that the displacement current should be properly included to have the current conservation. Then, what is the potential application field of this newly developed AC NGF tool? One application is the terahertz electronics. The conventional drift diffusion simulator intentionally neglects the time derivative of current density. Therefore, it cannot be applied to the terahertz frequency range. Since the AC NEGF is free from this restriction, it can be used to calculate the terahertz responses of extremely scaled electronic devices. As shown in right figures, the Y parameter shows a resonance behavior in the terahertz range, and the resonance frequency depends on various conditions. The AC-NGF solver can be used to investigate this topic. In order to calculate the small signal response, equations in the system should be fully coupled. By using the AC-NGF system at zero frequency, we can even improve the convergence behavior of the DC-NGF simulation. As shown in left figures, by using the fully coupled scheme, a quadratic convergence can be obtained. For more realistic results, phonon scattering mechanisms can be also considered in the NEGF simulation. In this case, two energy levels separated by the phonon energy are also coupled. Therefore, the overall size of a system of equation becomes huge. However, it is just a matter of numerical implementation, and the calculation can be done without any problem. We wanted to extend our approach to the noise simulation. The noise simulation becomes available only when the DC simulation and the AC simulation can be performed accurately. And now we have both simulation capabilities. Up to now, the state of the art in the noise simulation is the one with the multi-solvent BT solver. The NEGF level treatment is still missing, and I will work on this issue. Now, we consider the multi-solvent BT solver for non-uniform cross-sections. The gate-all-around MOSFET will be the next generation technology. In this technology, in order to reduce the resistance, wider source drain extension regions are intentionally introduced. And it is known that the shape of extension regions is very important. Since the MSBT solver is used as a reference tool for the drift diffusion solver, we wanted to simulate this structure with wide extension regions by using the MSBT solver. However, surprisingly enough, the MSBT solver cannot simulate such device structures. Usually, we divide the entire device structure into two subdomains, one for the MSBT and the other for the drift diffusion. Within the MSBT domain, it is assumed that a charge carrier keeps its subband index except during scattering events. In other words, different subbands are not coupled through the free streaming operator. Although the mode coupling is neglected in the MSBT solver, this effect is very important when cross-sections are non-uniform. As shown in the left figure, without the mode coupling effect, even the drain current itself is highly underestimated. Unfortunately, since the MSBT solver is a semi-classical solver, the mode coupling effect cannot be included in its free streaming operator. Therefore, we need an alternative approach. As shown in the table, there are several ways to implement the NEGF solver. The coupled mode NEGF is as accurate as the real space NEGF, but the uncoupled mode NEGF suffers from the same problem of the MSBT solver. So, our approach is to invent an intermediate one. The new NEGF solver provides us correct simulation result and can be easily related with the MSBT solver. In this new approach, the modus coupling effect is modeled as a self-energy. It is introduced to yield the same Lagrange function. since the lesser green function contains the energy spectrum of electron density, the electron density is preserved. These figures show some numerical result. The electron density can be reproduced properly. Now, it is not difficult to transform this NEGF solver to the MSBT solver. The self-energy can be regarded as a new scattering mechanism. With this geometric scattering, transition between different solvents can be considered as shown in these figures. Therefore, the MSBT solver now simulates a device with non-uniform cross-sections. Let me conclude my talk. Although the NEGF solver and MSBT solver are advanced, they were mainly restricted to the DC simulation. In this presentation, I presented two items to extend their simulation capabilities: small signal NEGF simulation and geometric scattering of a MSBT solver for non-uniform cross-sections. However, we have still missing simulation capabilities. In addition to the NEGF noise simulation and the NEGF surface roughness, the TCAD support for two-dimensional materials is urgently needed. According to TSMC's device architecture outlook, it is expected that two-dimensional materials will be eventually used in the transistor channel. Therefore, we must prepare TCAD for 2D material FETs. Frankly speaking, our TCAD community is not yet ready for 2D FETs, especially when they are integrated within the logic technology. The DFT NEGF simulation is very accurate, but it cannot be used in the TCAD simulation. On the other hand, simple approaches are sometimes too simple to capture physical mechanisms. In this sense, I guess that the Boltzmann transporter equation solver can be a good candidate. This animation shows an example of a graphene simulation result. By considering its energy band structure and scattering mechanisms, we can calculate the high field transport accurately. Okay, that's it for my presentation. And finally, I would like to thank my graduate students, especially Mr. Peter An has significantly contributed to the topics covered in my presentation. Thank you for your attention.